All right, so let's begin with joint hypothesis testing, and then we will extend it to overall hypothesis testing. Joint significance versus overall significance, right? So let's go over an example. Imagine we are regressing log salary, and this is a salary of a major league baseball player, right? So we are regressing baseball player salaries on years, which is years they're playing in the league, games year, average number of years, average number of games per year, and some performance measures. So what are the performance measures? This is a batting average, this is home runs per year, and this is runs batted in a year, right? So if you look at these, the three variables, the batting average, home runs per year, and this runs batted in a year, we can call them performance measures, right? So let's go ahead and call them performance measures of an athlete, of a baseball player, and let's see if we can answer this question or not. Imagine you want to test whether the performance measures, the one that we just called, have no effect on log salary, and i.e. we can think of them being excluded from the regression model, right? So if I want to test that hypothesis, how should I write the null versus alternative? So the null is going to be something like this. So I'm going to write null beta 3 is equal to beta 4 is equal to beta 5 is equal to 0, right? So this is a multiple linear restriction. So we have three restrictions here. If beta 3, the coefficient of batting average, is equal to 0, and collectively beta 4, the coefficient of home runs per year is equal to 0, and beta 5, the coefficient of runs batted in a year, is equal to 0. So this is going to be the null hypothesis. The alternative is if H null is not true, or at least one of them is different from 0, right? If even one of them, for example, beta 3 is not equal to 0, we're going to fail to reject the null. We're going to say that, okay, maybe two of them, no, we say that these three collectively are significant, okay? And let's go ahead and use Venn diagram to show this exclusion restrictions and try to figure out what are we doing. Okay, here imagine this is the log salary, and we have years and games, average number of games per year. I'm gonna go ahead and use another color, so let's use red. And the idea is that we want to see if the performance measures, I'm going to use red for performance measure. Imagine something like this. Are they something like this? Or look at the null hypothesis. We say that are they irrelevant or not? Or they're here. Or here. Right? So this is the question. We are wondering if these three collectively have something to do with your log salary in this example, right? Is it this one? Is it this one? Or is it this one? Okay, so this is a very interesting question, right? And how we try to answer this question. So for that, we need to define some terminology. So what is restricted model? What is unrestricted model? And then we're going to construct the test statistic together. The idea is that you cannot use t-stat anymore, because guys, remember, t-stat is for individual hypothesis testing. So if you want to test if beta 2 is equal to 0 or not, that's it. If you want to test if beta 1 is equal to 0 or not, or beta 5 is equal to 0 or not, right? If you want to test individual in these coefficients individually, we can use t-test. But if you want to test them collectively, jointly, we have to use something called f-test. So let's go ahead and construct that f-test together. Okay, so in terms of terminology, the model that we just cover, the full model, so let's call it the full version, the full model, okay? We call it unrestricted model because we're not imposing any restrictions. Does that make sense? So we can go ahead and estimate that unrestricted model. So this is a terminology that we are going to use. Unrestricted versus restricted. Unrestricted is the model that all the variables are there. The restricted are the ones that you're imposing some restrictions on them, right? So for instance, in the next model, you're going to see that I'm going to force the model to beta 3 and beta 4 and beta 5 to be equal to 0, and I call that model a restricted model, right? So let's go ahead and run this regression in R, and I'm going to give it a call. We call it reg_unrestricted. So this is the regression of our unrestricted model. Again, we're regressing log salary on these 5 coefficients, and this is the output. Look at the output. it seems that the number of years is significant at 1%. Look at that, the number of stars, the p-value is equal to less than 1%, right? So it says that at 1% significance level, the years, this variable is significant. This variable is also significant, you know, average number of games per year. But look at the performance measures individually. If I look at each of these performance measures individually, it seems that none of them individually is significant. This is important. So we can conclude that by looking at this output. So what I'm doing behind the scene, I'm calculating the t-stat and then compare the t-stat with the critical value, or use a p-value approach and say that if they're significant or not. But you know, here I can quickly look at the number of stars. There's no star here, so this means that it's not significant. So this variable, and this variable are not significant individually. So far you might think that you may want to go ahead and say, you know what, let's drop them all. So let's drop them all, i.e. let's say beta 3 is equal to beta 4 is equal to beta 5 is equal to 0. Well, sorry, individually, not collectively. So let's, again, if you only look at the t-stats, the individual tests, you might want to go ahead and drop them. But the point of this class is to, you know, answer this question. Even though they are individually insignificant, is there a chance that collectively they're significant or not? So this is a question that you're going to answer. You want to say that, is there a chance that these three are collectively significant, are jointly significant? Okay. And in order to answer that, as I said, we have to construct the F statistic. But let's see, what is that F statistic? Okay, so let's save some numbers here. So the number of observation is 3, in this example is 353, and this is what we call SSR UR. So SSR is the sum of score of residual, and UR, what is UR? Unrestricted. So I'm going to use subscript UR for unrestricted model and R for restricted model. So these two numbers are the ones that are really important for us to construct the F test, F statistic, right? So again, sum of score residual of the unrestricted model is 183. This is, you know, I rounded up to 2 decimals, I believe. And this is the R square of the unrestricted model, which is 62%. So if you look at the R square, this is 62%, and you can go ahead and calculate the sum of score of residuals as well. So what is this? This is a summation of your, let me actually write it this way, the summation of y minus y hat to the power of 2, right? Sum of score residual. These numbers, usually it's reported. You don't need to do it manually. There's no point doing that manually, okay? And so let's keep that in mind, these two numbers, okay? Sum of score of unrestricted model and R square. And if you want to visualize that, so in the Venn diagram, so where is that? This is, let's say, y, x1, x2, x3, x4, x5. So this part is going to be the SSR UR, sum of square of the unrestricted model. Let's say this number is 183. I'm going to go ahead and compare this number with the case that the 3 variables are dropped, right? So let me use another color. Remember, these are our performance measures, these 3. Okay. I'm going to go ahead and drop them. Let's go ahead and drop them. So this is my y variable, x1, x2, and now we drop those 3, right? And now look at the SSR for the restricted model. See, guys, remember, this is a restricted model, this is an unrestricted model. So obviously the SSR, the sum of score residual for the restricted model on the right, this is larger, right? So the idea is that how much larger is this number? Is this difference between the SSR of the unrestricted model and the restricted model on the right, is it significant or not, right? So I have to come up with a test statistic by looking at these two numbers, SSR of the unrestricted model and SSR of the restricted model. If that difference is so big, you know, it's statistically significant, what does it imply? What do you think? Exactly. That implies that those variables that you dropped, they were collectively significant because the amount of increase in SSR when you drop them was super high. Okay. So this is the unrestricted model. Now let's go ahead and look at the restricted model as well and run the regression for that. Okay. So this is a regression for restricted model. Again, what is a restriction? We have three restrictions here. Beta 3 is equal to 0, beta 4 is equal to 0, beta 5 is equal to 0. i.e. we are thinking that performance measures collectively are irrelevant, right? So here is a new regression line, a new regression equation. You see there is no trace of those three performance measures, right? So we regress in log salary on years and games per year, and average number of years in a year, games in a year. So look at that. Here's the output. When you look at the output, not surprisingly, all of them are still significant. We dropped the one that were not significant, right? So imagine we dropped the ones that were not significant. Okay, now what happened to SSR? The number of observation, of course, doesn't change. What happens to sum of square residual in the restricted model? It used to be 183, right? Now it is 198. Is it surprising? Not at all, right? Because look at that. Here, if this green shaded area is 183, then we know that it's going to increase. And in the new model, in the new regression, what was it? It was 198, right? So here it's 198. So we know that if we go ahead and drop these variables, SSR is going to increase, not surprisingly. Okay, so we're not surprised there. And we can also look at the R-squared version. So R-squared is going to decrease, right? This one is also not surprised. So let me go ahead and use another color. Let's use blue. If I want to show the R-square for the unrestricted model, these blue ones, the blue shaded area is a representation of R-squared, right? However, here, the blue shaded area is a representation of R-squared. So clearly, when I drop some variables, the R-squared is going to decrease. So SSR is going to increase, the green shaded area, but R-squared, the blue shaded area, is going to decrease when we drop, right? There's a relationship between the two. We can mathematically prove that. But we're going to go ahead and construct that F statistic by looking at the sum of square residuals, and then we're going to expand it to the R-squared version. Okay. So look at that. The sum of a square residual necessarily increases from 183 to 198. This is not surprising, but so here's the important question. Is this increase statistically significant or not? If it is statistically significant, it's a sign that we should have not dropped those three variables, because dropping them changed our sum of square residual or our squares dramatically. And again, everything is relative here, right? So when I say dramatically, it depends on what numbers you're looking at. Okay, so and here's the R-square of the restricted model. All right, now I want you to think about it. What is a good test statistic for testing if beta 3 and beta 4 and beta 5 is equal to 0? Let's see if we can construct that test statistic together. Okay. What do we know so far? We know that SSR unrestricted is, okay, going back to this slide, the green shaded area on the left is SSR unrestricted, and on the right it's the restricted version, right? So we know that SSR unrestricted is less than SSR restricted, and you're interested to see if the distance between the two is significant or not. So let's say I come up with a statistic. We don't have a name for that yet. So we say that, okay, let's look at the difference between the two, SSR restricted minus SSR unrestricted. Okay. So the difference between the two is not necessarily a good statistic, because depending on the unit of the random variables, you may get some very, very different numbers, right? So in one model, maybe the unit is going to remain dollars and etc. When you drop variables, the unit is going to change and the magnitude is going to change. So for that reason, we need to standardize this thing, right? So how do I standardize this? By dividing it by SSR of the unrestricted model. Okay. We're almost there. So if this number is big, if this statistic that I'm calculating is big, what does it imply? It implies that those variables that you dropped, were collectively important. You should have not dropped them. They were jointly significant, right? So again, this is a statistic we came up with, but however, in a statistic, if you want to come up with an unbiased version of these, to test a statistic that you're designing, you have to divide them by their degree of freedom. So the degree of freedom of the numerator is something we call Q. It's the number of restrictions. In this example, the number of restrictions is equal to 3. What does it mean, number of restrictions? Look at that. 1 restriction, 2 restrictions, and 3 restrictions. So Q is the number of restrictions. It's equal to 3. And in the denominator, this is the degree of freedom for our unrestricted model, which is n minus k minus 1. Right? So we came up with a statistic. Now we can give it a name. The name is F. So we call it F statistic. And this F statistic is going to have a distribution of F. Okay. So let's put all these things together. So here is the F statistic for joint significance test, right? So let me actually walk you through to the Venn diagram one more time quickly. So imagine this is the Y. I'm gonna stick with maybe fewer variables, maybe 3 of them. Okay, so this is x1, x2, x3. And I want to compare this with the restricted version. I'm going to go ahead and drop x1, x2, and x3, right? This is my SSR unrestricted. This is my SSR restricted. Not surprisingly, it's going to be bigger, right? Then if the difference between these two red shaded areas is large, it means that our F statistic is large. If F statistic is large, we reject the null. What was the null? Beta 2. So in this case, beta 2 is equal to beta 3 is equal to 0. Right, so this is our null here. Okay. And we are going to see that the distribution for this statistic is going to be F. So for those of you who are curious, where's this F distribution coming from with the degree of freedom of numerator, Q, and the denominator, n minus k minus 1. So if you're curious where this distribution, F distribution is coming from, remember, if you go back to our class number 6, when we talked about, it was a crash course in some, in statistics, we said F distribution is a combination of a chi-square in numerator with degree of freedom 1 and a chi-square in denominator with degree of freedom 2. And I know that chi-square is a summation of a bunch of normal distributions, right? This is as a side note, I'm not going to test you on that, but for those of you who are curious, where is this coming from? I just wanted to let you know that's where it's coming from, df1, df2. Okay, bunch of a squared version of a standard normal distributions divided by degree of freedom, and the whole thing divided by a bunch of squared version of the standard normal distribution divided by their own degree of freedom. What do we have? What is SSR? Sum of square of residual. So we are squaring the residuals. Residuals are normal. We are squaring those normals. So it's chi-square divided by sum of square of residual. The same story. Chi-square divided by chi-square. So what is the distribution of chi-square divided by chi-square? It's going to be F distribution. So this is where this F distribution is coming from. And again, why do I care about the distribution? Because if I know the distribution, I can go ahead and construct the rejection areas, right? So I know that it is F distribution. The good news about F distribution is that it's always positive, and the rejection area is always fixed. It's always right tail test. So we have, let's say this is my alpha, this is a critical value of alpha, and then here's going to be the rejection area. Basically, if you calculate this F, and that F was greater, so if F was greater than critical value of alpha, then we reject the null. Reject the null means that those coefficients collectively were significant. Okay. Okay. I want to show you another version of this equation for F statistic. The derivation is very easy. I'll leave it up to you. You go ahead and prove it. I'm gonna prove it in the class next time. But I want you to give it a try and see if you can prove it, but intuitively it's very easy. So let's say I look at the r squared version of these things. So this is the r squared representation of r squared, unrestricted model, and here this is a representation of r squared of restricted model, right? Which one is bigger? Obviously for unrestricted model is bigger. So we can prove that mathematically f is also equal to r squared of the unrestricted model minus r squared of the restricted model divide, so this whole thing divided by q, which is the number of restrictions, then divided by r squared, 1 minus r squared, unrestricted model divided by n minus k minus 1. Okay. Again, intuition is very straightforward. If you want to see if the change in this r squared is statistically significant or not, this is a standardized version of that change, right? We're dividing it by some number and dividing them by degrees of freedom. And mathematically, I want you to give it a try. Prove that these f statistic that we have in, here is the same as f statistic that we have here. Okay. And so hint, you should start from the definition of r squared. So you can think of it r squared 1 minus SSR divided by SST. Open it up and then see if we can use SSRs here, plug it here, and get back to this equation. Okay. All right. So the rest of it is very straightforward. So we say that intuitively how we construct this f statistic. Now we just plug in numbers, we look at that numbers, and then we will assign our significance level, and then look at the critical value. If f is greater than critical value, done. Okay. So here's a rejection rule that we already talked about. If f is greater than critical value, we're gonna reject the null, otherwise fail to reject the null. Okay. And how do we calculate this critical value? So there are two ways, like the one that we saw in for t statistic. You can look at the table in the textbook, or usually I don't know, you can Google these tables and etc. But I think this is a little dated nowadays. We don't use those tables for many reasons. First of all, it's not convenient. Secondly, it's not flexible. And so we are going to use R or Python or whatever programming language that you're going to work with. But in R, we use that quantile function. Do you remember? If it was t-stat, we said, okay, qt. Sorry, if it was t distribution, we said qt. Now this is f distribution, so we call it qf. So qf, the quantile of f distribution. Now we have to pass three numbers. The area to the left, which is, let's say, 95%, whatever. So here's 95%. Degree of freedom of numerator, which is the number of restriction. Degree of freedom of the denominator, which is the n minus k minus 1. The degree of freedom of the unrestricted model, right? So if you type this thing in R, you will get 2.76. So this is where the 2.76 is coming from. This is a critical value for when the alpha is equal to 5%, right? Again, in the next slide, I'm going to quickly show you how to use table from the textbook, but really, I don't recommend you to doing that. But just for the sake of argument, this is how you should do that. So first of all, look at the degrees of freedom, 3 and 60, and you have to look at the specific alpha. Okay, let's see if you can find this 2.76 in the table. Okay, so here's a table that's provided in the textbook or any other, I don't know, textbook or statistical packages that you're using. So what do we have? We have degrees of freedom of the numerator. I don't know why. Okay. Yeah, degree of freedom for the numerator, it was 3. Degree of freedom for the denominator, it was 60. And then this is a table for 5% critical value. So you can imagine how unflexible is this. So it means that for every significance level, you have to come up with another table. And what if my degree of freedom is 59? Look at that. There is no 59 here of the numerator. For that reason, we don't like this approach. It doesn't make any sense, especially these days that we have statistical packages, right? So we know the shape of the distribution, which is like this. We have the functional form. Now R is going to go ahead and calculate the integral for you very easily, and that's where we get the critical value. Okay. All right, now let's go back to our example. So if you remember, this was our baseball example, right? So baseball player salary. And we had a couple of numbers. So this sum score of the unrestricted model, 183, sum score of the restricted model, which was 198, and the degrees of freedom. So just remember, so let's do it here. So what is the degree of freedom for the unrestricted model? Degree of freedom of the unrestricted model is what? It's n minus k minus 1, 353 minus k. How many variables am I estimating? 1, 2, 3, 4, 5, 6. So minus 5 minus 1. So this is the degree of freedom for the unrestricted model, right? All right, now we have everything and we're ready to calculate the f-stat for that. So let's go ahead and look at the f-statistic. Guys, remember this is the SSR of the go ahead. Restricted model, which is larger, minus SSR of the unrestricted model, which is the smaller one, divided by Q. This is my Q, number of restrictions. Beta 3, beta 4, beta 5 is equal to 0, so 3 restrictions, divided by SSR unrestricted, and then this whole thing divided by degree of freedom. 353 minus 5 minus 1, right? This is the degree of freedom for the unrestricted model. We can go ahead and calculate this number is 9.55, and as you can guess, this is a large number. So we are right way in the right side of the tail. So maybe we are around here, 9 point something, 9.5. Okay, it's a very good news, right? Because when f is super large, it means that the idea that those coefficients were collectively irrelevant is nonsense, right? We can easily reject that idea. Okay, so formally, how do we do that? So we have to compare this critical value, this f statistic with the critical value. So let's go ahead and calculate the critical value for 1%. So if you do the critical value for 1%, it's going to be 3.83. Give it a try and see how we can do it in R. Remember, we had a formula for that, right? So here's a formula that you should use. This one, and I want you to give it a try and see if you can get the same number in R. So this is a f statistic approach, or we can do p-value approach. P-value approach is more informative, as we discussed it for single hypothesis testing as well. So the p-value approach, let me exaggerate a little bit and draw it here. So imagine this is my 9.55. I know it's way on the right, but let's exaggerate a little bit. So if I have my f statistic, I can back out the p-value, right? So p-value is going to be literally very close to 0. And what is the code for p-value? Again, we have done these things for the t-distribution. This story is exactly the same. It's a one-tailed test. So it's going to be 1 minus, this is p CDF, right, in R. CDF of f distribution. This is the f statistic, degree of freedom numerator, degree of freedom denominator. The answer is literally 0. Very good news, because guys, remember, when the p-value is small, we are happy. Going back to our case number 6, look at that. P-value is small, we're happy. F statistic is large, we're happy, right? So this is what we got here. We are happy means that we reject the null. So the 3 variables, so this means that we reject the null, so reject the null. And null was the performance measures are equal to 0, or irrelevant, right? Look at that. The 3 variables are jointly significant. So we reject the null that they're insignificant. They are collectively important to our equation. However, do you remember that we showed them that they're not significant individually when we tested them? So where did we see that? If I go back to the unrestricted model, here, we said maybe it's a good idea to drop them because they're not significant individually. Can you see that? There's no star here. However, as I discussed it in previous classes, do not jump into conclusion when they're not significant. So maybe something else is going on. Maybe they are collectively significant. So for that reason, we had to do the f-test. And f-test suggests that, yes, they were jointly significant. So what is the conclusion? The conclusion is that even though those performance measures are not individually significant, I will keep them in the model because they have a lot to say when it comes to when they're explaining some variation in the model collectively, right? So why do you think that's the case? The likely reason is multicollinearity between them. So we are going to use Venn diagram and show what's going on here. Actually, let me do it on the board. So this is my y variable, x1, x2, okay, y, x1, x2. And it seems that our performance measures were collectively significant, but individually insignificant. So most probably what's going on is something like this. We have multicollinearity, strong multicollinearity between them. So maybe something like this. Maybe it's something like this. So let's say this is x3, x4, and x5. If I want to calculate the beta head of x3, look at that. No, OLS is going to use only this area. Oh, sorry, you don't see that. Let's see. I think it's better now. Okay, so I already know that the variance of beta head 3 is very large. Why? Because OLS is using this small little shaded area. The same story for my beta head 4 and maybe my beta head 5. So I intended to make it even more collinear, that this number is small, but anyways, you get the idea. So this is my beta head 4, and this is my beta head 5. So because OLS is using a small amount of information in the red shaded areas, the variance of these coefficients are large. So this implies that the t-stat is small. Because remember, guys, what is t-stat? Beta hat divided by standard error. If standard error is large, t-stat is small. So this implies that x3 is insignificant. The same story for x4 and x5. Same story. Is insignificant because we have multicollinearity. However, look at them. Look at that. Collectively, they're explaining a lot. So for that reason, I prefer to keep them in the model. So collectively, x3, x4, and x5 explain a lot, right? A lot of y. So for that reason, we're going to keep them in the model. So how could we come to this conclusion? We look at the f-test. F-test was large, it was greater than the critical value, and then we rejected the null that they're irrelevant. Okay, so here, going back to slide, so this is what's happening behind the scene. Whenever the individual coefficients are not significant, but they're collectively significant, most probably the model is dealing with multicollinearity. And as we talked about in previous classes, multicollinearity is not the end of the world. It's no big deal as long as it's not hurting the model in terms of lowering the R-score, adjusted R-score. We keep them in the model, right? Because if I drop them, I'm going to make auto variable bias as well, right? So we already discussed about those things. Okay, so this was the theory and how we want to do it manually. In R, it's one line of code, so it cannot be easier. Okay, so well, to be fair, maybe 2 lines. You can make it 1 line. So the idea is that you have to save the unrestricted model in an object called regression unrestricted model. We already have this one, right? In the previous slide, we already have that. So this is your step 1. Calculate, run this regression, okay? And save it as reg underscore unrestricted. Step number 2, come up with your null hypothesis. In this case, the null hypothesis is this. Beta 3 is equal to beta 4 is equal to beta 5 is equal to 0, right? And step number 3, use this one line in R. So this is our step number 3. What is the line? The function is called linear hypothesis. So basically we are doing some linear hypothesis tests. You have to pass the regression model and your null hypothesis. I call it H0 null hypothesis. So what is the null hypothesis? This one. You're going to pass a vector. It's a C. It's a combination vector, right? It's a combination of these 3 restrictions. Restriction number 1, 2, 3. Guys, the name that you put here must be exactly the same as the name of the variable in the data set. So if I go back to maybe unrestricted model, Look at that. These are the names that the data come with. BAVG, HRON SYR, and RBI SYR, right? So these are the names. So we have to use exactly the same names here. And this is what we do. So sorry. So these are the exact names. And simply you say, okay, if it is equal to 0, if it is equal to 0, 0, 0. The reason that we cannot write beta 3 or beta 4 or beta 5, because R doesn't understand what is beta, because maybe you call it gamma, maybe you call it delta. So there is no beta anymore available in the data. However, we know R knows the name of the variable. So for that reason, it says that, okay, let's say BAVG is equal to 0. But the way that R reads it is the coefficient of BAVG. So you write something like this, and then R reads it like beta of BAVG is equal to 0. If I were the author of this package, instead of, I don't know, writing the name of the variables, I call it something like this. I don't know, beta, then underscore something. But maybe this is easier, more convenient, but you should be careful about it. When we say BAVG is equal to 0, we don't mean that the variable itself is 0. We mean that the coefficient is equal to 0, beta 3, beta BVG is equal to 0. Okay, so in these simple steps, this is the output. And let's go over the output and see how we should interpret that output. So the first number that you need to look into is maybe your F statistic and then the p-value. Do you remember we calculated these numbers manually in the previous slide? So my F statistic was 9.55 and the p-value was literally close to 0. We don't need to do it manually again in practice, but for exam purposes, I want you to learn how to use this equation because it is important. Okay. So look at that, the F statistic is 9.55 and the p-value is literally 0. Good news, reject the null. So reject the null. Right, and what are other numbers? So model number 1 is our restricted model, when we drop those 3 variables. Model number 2 is the unrestricted model, when we're regressing log salary on everything, 1, 2, 3, 4, 5 variables, right? And then for model number 1, we have degrees of freedom, n minus k minus 1. For model number 2, it's n minus k minus 1 plus q, because we're adding back those restrictions, right? And then this is SSR of the restricted model, SSR of the unrestricted model, right? So we already have these numbers, and look at those numbers as well, okay? I want you to go ahead and, well, actually we have done that. So there's an exercise I'll leave you with in the next video probably, that I want to confirm these numbers manually at least once. Okay, so let's pause the video here. In the next one, we're going to talk about overall significance.